welcome all the participants. I welcome our session leader, Dr. Suresh Mikhili, sir. Welcome, sir. Good afternoon.
Yeah, thank you, madam.
Okay, sir. So I kindly request to you, please start your session.
Yeah, good afternoon, Anna. Is the screen visible?
Yes, sir. Yes, sir.
Okay, ma'am, thank you. Mm. See, last 2 days, what we have discussed is, so first we have discussed about the architecture of the grid. Then after that, installation capacities we have seen. The last class we have seen about the history and significance of renewable energy systems we have seen. Then after that, what materials has been used in the PV systems, mathematical modeling of PV cell we have seen, PV module we have seen. So today we are going to see mathematical modeling of PV array configurations and some numericals we will try to see. If possible, rather than standalone systems, I will try to cover partial shading conditions. These two I am planning. The reason is both will be well connected. So mathematical modeling of PV array configurations and partial shading conditions will be covered today. Fine. So already yesterday we have discussed about mathematical modeling of single diode model, then mathematical modeling of PV array we have seen. Now, when the modules are connected in parallel, okay, two modules are connected in parallel, or three modules are connected in parallel, how the output characteristics we have seen. When uh, the two modules are connected in series, how the voltage will vary with respect to current we have seen. Then after that, from the PV cell 2 we have designed. So just I will recall you for a minute if you want. See, one cell we have taken with a value of 0.5 volts and 3 amperes. Okay, when it is connected in parallel, so you will have a voltage will be same 0.5 volts, but current will be added together. So 6 amperes you are getting. So when three modules are added in parallel, voltage will be same, but the currents will be added together. 9 amperes it is coming. So this is what for single cell, two cells, three cells. These are the characteristics of IV characteristic. Similarly, when the PV cells are connected in series. So two cells are connected in series. Here voltage will be added together 0.5 plus 0.5. So you are going to get 1 volt. But current through the cell will be same. So 3 amperes only you are getting. When even three cells are connected in series, the voltage will be added together 0.5 plus 0.5 plus 0.5 it is 1.5 and output current is 3 amperes. So this is what we have seen. After that what we have done, since we have taken one module 0.5 volts and 3 amperes, later we have converted one PV cell into module. What is a module? A combination of n number of the PV cells will be taken, which can be connected in series parallel. So here what we have taken, 5 strings we have taken. So 5 strings in parallel and 8 strings in series we have taken. When 8 strings are connected in series, the voltage will be 0.5 into 8, it is 4 volts. When 5 strings are connected in parallel network, so currents will be added together 3 into 5. So it is the 15 amperes. That's what we have seen yesterday already. So then we have also seen about when the multiple PV modules are connected, series parallel combination. Here current is same, but voltage will be added together 4 plus 4, 8 volts. And when two arrays are connected in parallel, then what will happen? 15 plus 15, 30 amperes. So these simulations also we have seen. Even after that, we have seen performance indices parameters. What is that? The mismatch loss, the fill factor, how will be calculated, and efficiency, how to calculate. So mismatch loss is difference of uniform condition power calculated, maximum power calculated at uniform condition minus the maximum power tracked at shading condition with respect to uniform condition into 100 will give you mismatch power loss. Fill factor is the maximum power extracted under ideal condition with respect to operating conditions like VOC, ISC is fill factor. Fill factor means how much amount of the energy you are able to extract on how much amount of irradiance is fallen on the modules. That is a fill factor. Okay. Efficiency, how we are calculating output power by input power. Here output power is V naught into I naught. Input power is, I have told you, the incident energy, how much amount of irradiance falling on how much amount of area. So these numericals we have already solved. Okay. So today we will try to see the PV array configurations are there. So after that we will come back to a few numericals, we will solve it. Okay. So I will come back here. So first we will try to see when we consider this is actually, so try to understand, this is a solar PV park is there. Is a, it can be modules are connected, can be in a series, parallel. So we are having a solar park which consists of the PV modules are arranged in different fashions. Now what happened, so there is a shading is happened on the module, like it can be cloud or it can be due to some other parameters, there is a shading is happened. So when during the shading conditions, what we will see is the first one. So different type of shadings can happen, which I'm going to explain you. Like uneven row shading can happen. One row, fully one row can be shaded, or one full column of one row, full the entire row of these modules can be shaded, or full one column can be shaded, or diagonal modules can be shaded. Okay, there are center shading can be happen, random shading can be happen. I will explain you each and every shading condition when the topic comes. Then so these shading conditions are examined in different topologies, it can be connected. So that configurations today we are going to see. It can be connected in series, parallel, bridge link, honeycomb, TCT, different conditions will be there. I'll try to explain you that. Then now when I consider different shading conditions and on different PV configurations, output characteristics can be measured. Okay, so that is IVPV cost can be measured. So when you can measure the IVPV cost from their voltages, currents and powers when we calculate, so output parameters what can be analyzed is from the circuits, open circuit voltage, short circuit current, global maximum power point parameters, local maximum power points, number of peaks, fill factor, mismatching loss, efficiency. These all parameters can be solved actually in the system. So when we have PV system is there, when shading is happen, different shading can be happen. So when PV modules are connected in different configurations, what we are going to see is we are going to analyze how the IVPV characteristics. These simulations I will show you on the last day. Okay. Now, when the simulation has done, you are got IVPV characteristics for different shading condition. During that period, what is the open circuit voltage? Different parameters can be examined. Okay, the finally you are going to calculate efficiency of the system, mismatching power loss and fill factor will be solved. This is the main motto of next 2 days. So the first, let me give you different shading conditions, how it will happen. Okay, then after that I will go to configurations. Suppose when you consider the system, you see, so now PV panels are first one. When you observe, what is that? See, there is a partial shading condition is available. Okay, when there is a partial shading condition is there, what is that? Due to one, you see, there is some modules are shaded by some of the elements. There is a trees can be, because of trees there is a shading can happen. Because of tall buildings, yes, shading can happen. Shading can happen due to tall buildings. Shading can happen due to clouds. Shading can happen due to nearby trees. Shading can happen due to even some snow fallen on it. Even some snow. If you observe here clearly, there is a snow is fallen on here. There is a snow is here. So first one is, if you go to some areas, there is a wherever you are considering PV modules, there is a possibility snow can be accumulated on the panels. Due to snow, also shading will happen. Even during evening times or during cloudy days, there is a possibility. So there is shading can happen due to clouds. The height of the system is very less, and the trees which are nearby, the PV panels are height is higher than the PV panels. Then what will happen? Shading will happen due to trees. There is a possibility shading can happen if your PV panel height is less. Next to your house, there is a tallest building is there. Try to understand. Yours is a 5-story building. Next to your house, 10th-story building is there. Then definitely that shade will fall on your PV panels. I hope you understand. So these are the realistic scenarios. Okay, our rooftop PV system you construct. Let us suppose on your roof itself, your wall is very big height. So there is a possibility, there is a shading can happen from your wall side also. Now we will see some practical situation. I am considering, so there is a 6 by 6 system is there. There are 36 PV panels I have taken. 6 by system is there. Now, what I'm assuming is this is called a column shading. How many columns are there? There is one, two. How many strings are there? One, two, three, four. There are 6 strings are there. Okay, and each string we have 6 more PV panels are there. That means the array is 6 by 6 structure, and then each string is a series parallel structure. In each string, how many are there? 6 PV modules are connected. Now what happened? Suppose you have a building is like this. One wall is here. Suppose here up to this particular point, there is some wall or some shading is happened. So now what I'm assuming is, as I said, there is no shading 1000 watt per meter square. If it is the highest amount of shading is there, that means highest amount of darkness will give you lowest amount of irradiance. Okay, highest amount of shading will give you lowest amount of irradiance. So here next to your wall, you consider this condition. These two panels are highly shaded. Okay, then what happens? 200 watt per meter square can be observed. Next two panels are little bit of less shaded. I can consider it can be maybe 500 watt per meter square, or it can be maybe 400 watt per meter square. Next panels are little bit of less shaded, that is 500. Next one. So what I want to tell you is, so from highest worst shading to the lowest shading. So highest shading is there, low irradiance. The medium shading, medium irradiance. Low amount of shading is there. Here I can observe there is 900 watt per meter square. So shading may vary. This is called the column shading. This is called column shading. There is a possibility even row shading also can happen. Suppose if you assume that, so from this side shade is coming, only this much amount of wall is there. If this much amount of wall is there, like this shading can happen. So there is 200 watt per meter square, 300 watt per meter square, 500 watt per meter square, 7, 8, 9, and remaining everything is 1000 watt per meter square will take. This is called a row shading. There is a possibility entire row can be of same amount of irradiance also can be there. Try to understand. The height of your wall is same height. Then all the modules can be of with all one row modules can be also with 500 watt per meter square can be taken. Just to make you understand, I have taken different irradiances. Otherwise, if you have a wall, a full wall is there. If you have consider a full wall is there, a full wall, full shading is happened. All these row modules can be shaded with single value. It can be, the first row can be with 200 watt per meter square, second full one with 500 watt per meter square. As per the irradiance, it can happen also. If different heights of wall is there, the stepwise height, like if you take, there is a stepwise wall is there, then there is this type of possibility will happen, different irradiances. Or the wall structure is completely same height, then all these panels will exhibit same amount of irradiance levels. So first one is column shading, second one is the row shading can happen. There is a possibility nearby nearby your house there is a electric pole you consider. Let us suppose some electrical big pole or big rod is there, or big tower is there nearby your house. Tower structure, how it will be? If you consider a tower structure, which one? Some the communication tower, telephone tower is there. So at the down there is high, the width is more. If you go top, width is less is there. So that's why there is a possibility wherever the lowest width is high, then their shading is high, then lower radiance. Top, then there is a possibility what shading can be. So like this also shading can happen. This is called diagonal shading. Okay. But even if it is a constant height is there, then there is a possibility all can be shaded with only one irradiance value. So on the rooftop, when you consider your PV modules, you need to make sure that the shading should not happen, and you need to take a call like, so it is properly installed without any shading. If shading will happen, what will happen? The current flowing through this one will changes, and voltage across the elements also will change, current will change, obviously power will change. The problem with the partial shading condition is when there is a shading happen on any of the modules, the current flowing through the modules will be changing, and voltage across the modules will also will change, so that obviously power will be reduced. You can't get extract the maximum power, you will extract very small amount of power. So there is a possibility you have a building like this structure, wall is there, both the side wall is there. Okay, so there is triangular shading can happen. So there is, okay, triangular shading means, so here height wise it has come, here height wise it has come, here also height wise is there, but without height the constant height is there, both the sides of same height is there, then there is L shape shading also can happen, center shading also can happen. Or if tree structure you take, now you take this tree structure, this is called random shading can happen. Now you see, if you observe here in the corner, if this building is there, how much shading is happened? From this corner to this much part is happened, remaining part is okay. So these type of things are diagonal shading may happen. Where whenever the clouds are there, it is a random shading. When the clouds are there, it is a random shading. Okay, so then even tree structure is a random shading. Okay, and when we have this one, which one? Buildings are there, sometimes based on the structure height of the building. So here you see, here height is more, here height is less, based on that one. Here also what will happen? Triangular shading can form, column shading can happen, row shading can happen. So you need to consider in a proper way. Okay, now if the shading is changes, how the IV curve, current and voltage will change, how the PV curves will change, I want to show you. So suppose I have considered one cell I have taken, one PV module or one PV cell I have taken. Okay, so when I have taken one PV cell, what happened? One PV cell or one PV module, it is of 250 watt per meter square I have taken. If it is of 250 watt per meter square, it gives you how much? The voltage of 330 volts, current of how much it is giving? Same like previously. Same like when the panels are connected in series or parallel connection, I have shown you. No? So here, this is also simulated results. So this is IV characteristics I have taken. Now I am going to show you these things. I will simulate and I'll show you anyway tomorrow or after tomorrow. But let me show you first. So when irradiance is 250 watt per meter square, so then what is happening is when irradiance is the radiance is 250 watt per meter square. So this is the curve we are getting. So here current is approximately 3 amperes. I am getting 330 volts. When irradiance is increased to, that means 250 watt per meter square is highest shading happen. When 500 watt per meter square is there. It is going to give you how much? There is up to 10 amperes it is giving. So when there is 750 watt per meter square, it is giving you 15 amperes, 330 or 340 volts. When 1000 watt per meter square is there, then it is going to give you 20 amperes, sorry, 20 kilowatt power, 20 kilowatt power and 330. Okay, this is what PV curves. It is called P versus power versus voltage. Okay, this is PV curve. Next one is IV curve. IV curves we have already drawn. The current versus voltage. So the current versus voltage is, if you observe, 250 watt per square meter is there. So at 250 watt per square meter, how much amount of current is there? 20 amperes is there. How much amount of voltage is there? Maybe 330 is there. So how much amount of power can be generated? Voltage into current, if you multiply, this one I will get. Okay, so similarly at at so approximately it is, do you understand? I hope so. Next one we will try to consider. Next one is 500 watt per meter square, so 40 amperes, but this is the point. It is not exactly this much only. It's not 40, 38 or something will be taken. Okay, now so these are the global maximas. When you consider calculate the power, you need to consider this is the VOC, this is VOC, this is VOC point, and for this is VOC. ISC is this one. When you consider global maxima is, this is in this curve, this is the maximum point, isn't it? So this is the point your VOC is there. This is the point ISC is there. Okay, when VOC ISC, if you multiply, you will get this power. That's why you will get 5 kilowatt, 10 kilowatt, 15 kilowatt, 20 kilowatt you are getting. You hope you understand. When the irradiance is changing from 250 watt per meter square to 1000 watt per meter square, what happened? Currents are increasing, voltage is constant. So current is increased. When 250 watt per meter square, 20. When 500 watt per meter square, 40. When 750 watt per meter square, then is 60 amperes or 80 amps. Or consider in a reverse. Consider in a reverse. Okay. So what is that? Reverse we will take. We'll try to understand. Suppose you have no irradiance is there, 1000 watt per meter square. You are getting 80 amperes. When 25% shaded, 25% shaded means 750 watt per meter square is giving. So 60 you are getting. When 50% shaded, out of 80 you are going to get 40 only. When 75% shaded, then 250 watt per meter square you are going to get 20 amperes. Accordingly, the powers are calculated. So when irradiance is changing, when shading conditions are changed, then there is a huge change in voltages, currents and powers. But second one, when temperature is varying, this is irradiance is varying. Second one, when temperature is varying, what will happen? You try to see. Second graph I'll explain you first. Even though temperature is varied, but one is at 0 degrees, this is at 0 degrees, second curve is 25 degrees, third curve is 50 degrees, fourth one is 75 degrees. So temperature is increased from 0 degrees to 75 degrees, but your current is constant. Voltage is a little small amount will change. These are the simulation results. I will show you. With the increase in temperature, you see here, with the increase in temperature, if temperature is increasing from 0 to 75, the voltage is decreases. But current is almost constant, little change is there. First one is 0 degrees, this is 25 degrees, third one is 50 degrees, fourth one is 75 degrees. Now, if you increase the temperature, little bit of voltage change decrease is there, but constant current is there. So because of which the powers are not affected much. but I want to extract the maximum power. If I want to extract a maximum power, even though your temperature is 0 degrees or 75 degrees, not a matter at all, but how much amount of the light intensity in the nature, how much temperature is there is not a matter, how much amount of irradiance is falling on the PV panels is matter. I hope you understand. In the climate, how much temperature is there is not a matter, but how much amount of irradiance is falling on the panels is very very important. By varying the irradiance from low to high, there is improvement in the current increase is there. The powers are increased, even currents are increased, but even temperature is increasing, it is constant, it is executing. This is what I want to tell you first. I hope you understand. Okay. Any queries? Someone is typing. No. Okay. I hope this one you understand. So what I meant to tell you, when the irradiance is changing, currents will change. Obviously, power extraction will increase when the shading is less. When shading is more, current extraction is less and power will be less. But when temperature is either increasing or decreasing, there is no matter at all. So same amount of current and same amount of power will be there. Okay. If we have constant irradiance conditions, this is happening. Now, suppose what are the techniques we are having to mitigate adverse effects in the partial shading conditions? Okay, what are the techniques we are having to mitigate these effects? We will see. The first one is we have a different PV topologies are there. Okay, and we have MPPT techniques also there. What is that? We can use bypass diodes as well as blocking diodes. First one is that to avoid, okay, to extract the maximum power. So we can use bypass and blocking diodes, PV array configurations, PV array reconfiguration, PV architectures properly can be considered, and even you can consider different MPP techniques for all these configurations, reconfigurations. We can consider these MPP techniques to extract the maximum power. Okay, so how we will mitigate the partial shading effect is by considering bypass and blocking diodes, or different PV configurations can be considered, reconfiguration can be taken, PV different architectures can be considered, or else for all these configurations or reconfigurations or different architectures, we can use MPPT techniques. What is MPPT? Maximum power point tracking techniques. We have conventional MPPT techniques are there, intelligent. You might have heard about P and O, incremental conductance. Those are comes under conventional MPPT techniques. So intelligent means already yesterday we have discussed about this AI based, just as so fuzzy logic based, sliding mode control based, okay, neural network based MPPT techniques. So these are called intelligent techniques. Optimization techniques are PSO based, particle sway optimization based, Grey-Wolf optimization, okay, and we call optimization, sliding mode optimization, hybrid slide mode optimization. So there are different types of optimization techniques also available. Okay, even cuckoo search is there. Along with that, hybrid configuration, hybrid MPP techniques are there. Hybrid MPP techniques means combination of any of the two, a conventional intelligent or conventional optimization, intelligent optimization. So we have different optimization techniques are there. The research scholars who are working on it to improve the efficiency. Okay. Now let me show you. First, I will try to give you about bypass diodes. So how the bypass diodes will be considered, I will show you. Now see. So here we have two things are there. One is blocking diode, second one is bypass diode. These are blocking diodes and this is bypass diode. You understand? This is one PV modules when you consider. Okay. The diode across the PV module which you are considering is bypass diode. The diode which is considered for a string is one string is there. For every string, one on every string, one blocking diode will be considered. So based on number of parallel strings, number of blocking diodes will be equal to number of parallel strings. How many are there? That many blocking diodes will be there. Excuse me. Okay. So number of bypass diodes will be equal to number of total modules in your PV system. So number of blocking diodes will be equal to number of parallel strings. How many are there? Number of bypass diodes will be number of total modules in the PV cell. How many are there? That many bypass diodes will be there. Now we will try to see what is the significance of both the diodes. We will try to see, then I will come back to that each and everything. So now, so when we consider bypass diodes which are linked, now can you observe, bypass diodes are where we are considering, bypass diodes are linked in parallel with the POV modules, and blocking diodes are connected in series with the PV string. Okay, bypass diodes are connected in parallel with the PV modules, and blocking diodes are connected in series with the PV string. Okay, why we are using? To prevent the reverse passage of current through the shaded modules. Suppose any module is shaded, the current should not, if shaded is in the sense the fully shaded, highest amount of current, if it, current can pass through it, no, through the shaded module. So to avoid that reverse passage of current, we are using blocking diodes. So if you use here blocking diode, what will happen? If any module is shaded, if I use, the current is passing through this way. If any reversal current, if it want to flow through this module, it will not flow. This blocking diode will do that purpose, if you understand. Okay, so when we consider the blocking diode, see, try to understand. So this is the blocking diode which will allow normal flow of current, whereas if any module is shaded, any one of the module is shaded, it will not allow the reversal flow of current. So that is the main advantage of the blocking diode. Okay. Next, under normal conditions, uniform irradiance condition or homogeneous or uniform irradiance, that means all the modules with 1000 watt per meter square is there, then bypass diode will not conduct. It will be in reverse bias. All are 1000 watt per meter square. So there is no shading at all. Uniform irradiance condition. All modules with 1000 watt per meter square. You no need of any bypass diode. Okay. In case of non-uniform condition or partial shading conditions, okay, then bypass diodes need to be in conducting mode. Why? Which should not allow. I'll show you. So it serves two purposes, bypass diodes. One is ensuring PV modules is safeguarded from the hot spot issue. Second one is minimize the voltage drop in the shaded cells. Okay, it will restrict the reverse voltage in between 0.4 to 0.7 volts. Okay, then the power consumption of the shaded module also will be reduced. Okay, so if the power consumption will reduce in the sense the heat will be reduced on the shaded module, so hence the span will increase. Okay, now you try to see, let me show you here. So when all are with uniform irradiance conditions, the power is flowing this way. So there is no need of bypass diodes. If any one module is shaded, how it will be, I will show you its effect. Okay. So now here what will happen, the next slide it will come. So now during normal conditions, unshaded condition, this is the first one. During uniform condition, what happened? You are getting the proper peak, you are getting IVPV characteristics, only you will get single peak, it is called global maximum. Whereas if suppose if there is any shading is happen on any of the modules, what will happen? So the current flowing through the string will not be equal. So what happened? There is the multiple peaks will come. These are called local maxima. What is local maxima? Due to partial shaded modules, what will happen? You are not going to get uniform irradiance. During unshaded condition, during uniform condition only, you are get global maxima. This is the global maxima. That means how much amount of VOC, how much amount of high short circuit condition is there, that much amount of power can be extracted, that much amount of voltage and current can be measured during uniform condition. If any of the modules are shaded, then what will happen? There is a possibility current flowing through the each string will not be equal. If current flowing through the each string is not equal, the power calculation of each string may not be same. So you will experience there is the multiple peaks in the system. Okay, so to avoid the multiple peaks, to extract the maximum power, so these things need to be eliminated. We are using MPPT techniques, maximum power point techniques. Okay, so now let me show you this example. First one, PV array with blocking diode. If consider blocking diode not there, if consider first one blocking diode not there, so this is the uniform condition we are getting. If blocking diodes are there, like this we are getting. So now what will happen? Now this is unshaded module 1000 watt per meter square, and this is the blocking diode, this is a bypass diode. Now what I'm doing, I'm using bypass diode in such a way that the current, how it will flow, it is flowing like this, it will not flow here. During normal condition it is flowing like this if it is unshaded, but during shading condition it tries to flow through the bypass diode, then through it. I hope you understand. Okay, what is this here? Okay, I hope you understand. When any module is shaded, then what will happen? The current will try to flow through the bypass diode, and it will avoid, it will go. Then that time only the use of bypass diode will happen. Okay. Now we'll try to see. Under standard test condition, what is STC? 1000 watt per meter square you have taken. All the modules are not shaded. All the modules are at uniform condition. At uniform condition, you are going to get global maximum. This is global maximum, normal condition. Suppose if the modules are shaded, then what will happen? If entire current is flowing through this during when modules are shaded, then you will get this condition. Understood? I hope you understand. Now, at least here what happened with the bypass diodes with two curves, two maximas I got. Okay, without bypass diode, very small amount only I can extract. With the bypass diode, little bit more I can extract. Now, right on. So first one is STC condition. During STC condition, what happened? During standard test conditions, so what happened? The first one is we are extracting maximum power. With the bypass diodes, if we use bypass diodes, then one module we have avoided. So what will happen? We can't extract that much amount of power. Little bit small will be there. If the current is flowing through the shaded module, still further less amount will be there. So we will use MPPT technique. Now this one will be avoided. It tries to improve, it tries to maximize the power with the help of MPPT or reconfigurations techniques. Okay. No, we have different series configurations are there. We have different configurations are there. It can be modules can be series connected. Modules can be connected in parallel. Modules can be connected in series parallel. We will try to see. Suppose if the modules, I am considering 7 by 7 structure. Okay. Now in a 7 by 7 structure, how many modules will be there? There are 7 by 7 structure. 49 modules are there. What is the series configuration? All PV modules are connected in series. First one is connected in series with second one connected in series with third. So all these modules, seventh module is connected in series with eighth one. 1 to 2, 2 to 3, 3 to 4. So 7 to 8, then 14, From 14 it goes to 15. So in this case, in the series configuration, all the 49 modules are connected in series. When we will use this application? Any guess? So in the series configuration, what has happened? The currents are flowing through the IPV array will be equal to I1 module. Even though 49 modules are there, the current will be equal to what? Total PV current will be equal to module current. So the current flowing through the PV system will be equal to one module current. Either it can be IM1, IM2, IM3, IM49. But what about the voltages? Voltages are a summation of VPB is equal to V1 plus V2 plus V3 and so on, V49, 49 into Vm. So it is under uniform shading condition, 49 times one module. That means the current, in the sense, current is one module current. If it is series configuration system, even though 49 modules are there, current will be equal to single module current. The voltage will be equal to number of modules into module voltage. So series configuration will be used for high voltage low current applications. When you have a high voltage is required of low current application, high voltage low current applications, you can use a series configuration. Hope you understand. Now to calculate IV PV curves, I need to use the XY graphs of IV curve. The PV curves has to be used. Voltage measurement, current measurement need to be considered. Okay. So now how the PPV will be calculated? VPV into IPV is PPV. It will be same. The 49 into Vm into, try to understand. Here PPV into VPV is how much it will be? It will be equal to how much? PPV into VPV value. Okay. Now parallel configuration we will see. So here how much we are getting? 49 into Vm into Im. Now in the parallel configuration, you know very well, in the parallel configuration the voltage will be same. Voltage will be equal to one module. All the modules are connected in parallel. If all the modules are connected in parallel, what will happen? The voltage of the VP will be equal to the voltages of single module. It is a low voltage application. What about current? All the modules are connected in series. All the modules are connected in series. So the currents will be added together. So your current will be how much? 49 into Im. Voltage will be Vm. The current will be, all the modules are added together, 49 into 49 modules into Im. So it is, the power will be again VPV into IPV, which is equal to Vm into 49 into Im. It will be 49 Vm Im. So power will not change. Either it is series connected or parallel connected. Power is same, 49 Vm Im only. But series configuration is used for which one? Low current, high voltage application, and parallel configuration is used for low voltage, high current application. Whereas powers are, both the powers are same. You try to understand. Now, same 49 modules I have given to you. If I ask you to design for medium voltage, medium current application, what we will do? Next one is series parallel configuration. Here, what we will do? Here, in the series parallel configuration, so there are the first one. This is called array. In first array, all the modules are connected in series. Try to understand. There are 1 to 7 modules are connected in series. There is a second array. All the modules are connected in 7 modules connected in series. So like this, there are 7 arrays are there. 7. So in each string, there are 7 strings are there. Each string, 7 modules are connected in series. Okay. Second string also 7 modules connected in series. So like this, 7 strings are there. In each string, all the modules are connected in series. but all the strings are, if you observe, all the strings are connected in parallel. The series parallel configuration, what we are doing, seven strings are connected in series. Sorry, seven modules are connected in series, and seven strings are connected in parallel. So what about the voltage? When seven strings are connected in series, then what about the voltage? Voltage will be summation of PV1 plus PV2 plus PV3 plus PV4, PV5, PV6, PV7. 7 Vm. The voltage will be equal to 7 times Vm. If I calculate across this, 43 plus 44 voltage, V45, V46 and so on, V49. That means the VPV is 7 times the module voltage. What about the current? The current is summation of string current. Current is a summation of string current. How many strings are there? There are 7 strings are there. In each string, what current will flow? In each string, the module current only flowing. So the summation of current will be IPV will be equal to how much? I string 1 plus I string 2, I string 3, I string 4, I string 5, I string 6, I string 7. So string current and the current flowing through the entire string will be what? When the modules are connected in series, the current flowing through all the series modules will be equal to what? Is a current of one module. So string current is equal to one module current. So IPV is equal to I string 1 plus I string 2 current, I string 3 and so on, I string 7, which is equal to 7 times I string value, which is nothing but 7 times IM value. So PPV will be equal to how much? PPV will be VPV into IPV, 7 VM into 7 times IM, which is equal to what? 49 VM IM. So what I want to tell you is, when 49 modules are there, when 49 modules are connected in series configuration, you are going to get high voltage, low current application, which is powers are the product of the current flowing through the module and the voltage across all the modules will be taken. That is 49 VMIM if 49 modules if I take. If parallel connected structure, if I consider, the voltage across each module will be same since it is parallel connected, but currents are added together. So currents will be 49 IM, so it will be 49 times VMIM. Now, when the modules are connected in series parallel combination, then what will happen? In the series parallel combination, what we are doing, the strings are connected. Each string is connected in parallel with another string. In a string, modules are connected in series. In a string, modules are connected in series and strings are connected in parallel combination. So this is what VPV is, the summation of voltages in the modules in the string, and currents are the summation of string currents. So you are going to get same amount of power, 7 Vm into 7 Im, you are going to get 49 Im into Vm only. Okay, but when the problem will come, during uniform irradiance condition, all the shading parameters will give you same amount of power will give. But if any one module is shaded, try to understand. Now series configuration you take. Any one module is shaded, the current will be changing. Obviously power will go away. The current flowing through that entire all 49 modules will be decided by shaded module. I hope you understand. Now, if it is a parallel connected, any one module is shaded, the voltage across the entire string will be decided by the shaded module only. So it should not be series connected, it should not be parallel connected. So if you connect in series parallel configuration, even though it is any one module is shaded in any of the string, or in any of the module is or in any string or anywhere it is the shading is happened, then there is no issue. The currents and these things can be easily, can be better way you can extract. Okay. Now there is, there are some researchers are working on it. See, rather than series parallel, why can't we consider all are connected together? Okay, the people have considered series parallel, and there is later is this one. Why can't we consider? Why can't we consider all the points are connected? So previously series parallel was there. Now what they have done? All the modules are connected together. All the modules are connected together. It is called total cross state. Previously, this is one string. This string is connected parallel with other strings. Okay, in a string, all modules are in series contact. So that was series parallel. To the series parallel, what they have done? All these modules are tied together. You observe. This is called total cross state. Here the advantage is what? If it is a total cross state configuration, the voltages will be taken as, this is the first row. If you observe, this is the first row, row 1 voltage. This is the second row, plus row 2, row 3, row 4, row 5, row 6, row 7. How many rows are there? There are 7 rows are there. The current will be calculated, sorry, voltage will be calculated. How it will be calculated? So the voltage across each row, this is a parallel combination. Voltage across each row will be same, that is VR1. Voltage across the second row, entire thing will be same, this is VR2. Voltage across the third row is VR3. Voltage across fourth row is this one, fifth, sixth, seventh, because all are connected together. So it is VR1 equal to VR2 equal to VR3, VR4, VR7 equal to VM. So PPV is a summation of VR1 plus VR2, VR3 and so VR7. That is nothing but 7VM. It is also 7VM. Now what about the currents? What about the currents? The currents are, now this side you take. These are all are connected now. Sorry, this one. Now, currents if I consider, what I am considering, this one you consider. This is string, one string, first string, the current flowing through the first string, plus current flowing through the second one, current flowing through the fourth one. So, what can be taken is IM1 plus IM2, IM3, IM4, IM5. Okay. So when we consider the currents like this, module 1, module 2 current, module 3, module 4, so like this can be taken. Here why we have taken module 1, module 8 current, module 15th current, module 22 current, module 29, module, this is 36, module 43. All these module currents are added together, then it will give you 7 am. So power will be 49 times of IM only. So here, what is the advantage of, see, total cross state is the one of the best conventional configuration compared to remaining all configurations. Why? The reason is, now, the previous module you take, I told you already, any one series configuration, any one module is shaded. Any one module is shaded. Entire current flowing through the, all the modules will be decided by that module only. Okay. So lowest amount of current will be flowing, then there will be a problem. See, and one more thing, any one of the module is shaded. The voltage across the string also will change in the parallel connection. But now, If you take series parallel connection, in the series parallel connection also similar scenario. What happened? Here also there are 7 modules are connected in series, 7 strings are connected in parallel, like that it is there. Any here also what is happening is, compared to series and parallel, series parallel is better, but compared to TCD, series parallel is not best. Why I'll tell you. If any one module is shaded here, entire current flowing through the string will change. Any one of the module is shaded in the other string. Here, this one also will change. Any one module is shaded here. This one also will change because it is not tied. But now you see, in the TCT configuration, it is all are tied together. So there will be less effect on one each other. So here this one we will not take bypass diode we are using. So we will take from only these modules, or we will take only from these modules with a bypassing diodes. Suppose if this module is shaded, let us suppose, what I will take? I will take a current from this module and from bypassing, and power will be taken. So because we have so many connections are there, all are joined together, we can avoid a shaded module, and TCT is one of the best PV configuration or the threshold configuration which will be used by many of the people. Even people have, but here one drawback is there in the TCT. Since there is number of crosslinks are very high, since more number of joints you are using, there is a wiring losses will be very high, system is complex. Since you have used more number of crosslinks in the middle, so what happened? The wiring system complexity is high, and the wiring losses and conduction losses will be more due to these extra each and every joints. Okay, but there are other people who are working for PhD other things. There are some researchers who developed some concepts. So now there is a bridge link configuration also, it is there. What is meant by bridge link? It is modified version of TCT, or modified version of you can say like series parallel or TCT. Series parallel, in the series parallel, modules are connected in series, strings are parallel, but TCT combination, all are joined together. But in bridge link configuration, what they are doing is, what is nothing but a bridge? 4 modules together, it is called a bridge. So what they will do, these 4 modules together, one tie they will do. Next 4 they will take. They will not take alternate. They will take alternate one. They will not take this one. They will not take here. If I take here, it will become, if I take a tie here, so try to understand. I will draw here. You will understand more. Sorry. Let me draw here. You will understand better. So conversion of series parallel to bridge link, what I will do, this is here one tie I will put. I hope you understand. Different color I will take. So here one knot I will do. These 4 together, it gives you one combination. Okay. Okay. Next, I will leave one. Next, what I will do? Next, here I will put one knot. These 4 will be bridge. Next, here one knot. These 4 will be bridge. Next one will be alternate. I will leave that here. These 4 will be one bridge. Next, here. Next, here. Okay. I hope you understand. Okay. Series configuration, what we are doing is, these 2 are connected, these 4 together one bridge. Then here I will not take a knot. Then what we will do is, here one bridge link we will take. These 4 will be formed as a bridge. Next, alternative. These 4 will be formed as a bridge. And here I can't take. Next, when it comes here, if I draw here, it will become again TCT. I should avoid first one. So I will take next link. This 4 is a bridge. Next, I will not take here. Alternate. This is a bridge link. Next, I will not take here. This is a bridge link. Next, here, then here. The first one will be repeated like this. Then here, here. So the bridge link configuration is okay. Removal of alternate links. If you remove, that is a bridge link. If you remove alternate links, that is a bridge link combination. Or 4 bridges together, if I consider, that is also a bridge. Hope you understand. Okay. Here, what will happen? So it gives you better performance compared to series parallel, but less efficiency compared to TCT. It gives you the medium performance compared to series parallel. Bridge link is better compared to TCT. It little bit fall short. Okay, even bridge link configuration also people are using. So here the voltage, how it will be? Voltage will be summation of V1 plus V2 plus V3 the across all the 7 into Vm. Current also 7 into IF. This is also used for medium voltage, medium current application. Power will be same. Even bridge link, if you consider, also power will be same. Even there is one more configuration, conventional configuration people have considered for honeycomb configuration. That honeybee structure will be there. That is hexagonal structure. So there, how it is, 6 ties. After 6 they will do. That means here one alternative they have removed. No, here 2 they will remove. That's it. Not more than that. Okay. First one. After 6 modules, one link. One more. Here after leaving 6 modules, they will do one more link. So honeycomb configuration also gives you a little bit better than bridge link, then lesser than. So this is also 7x7 structure. So we have various. If PV panels are there, it can be connected in series for high voltage application, low current. Parallel is reverse application. What is that? Low voltage, high current application. Series parallel, medium voltage, medium current application. And bridge link, honeycomb and TCT also medium voltage, medium current application. Power, in all the cases it is same, but when shading conditions are there, TCT will give you the best performance compared to other configurations. Is it okay? Now, these are the basic. If you observe, first one series parallel, second one is TCT, next one is bridge link, next one is honeycomb. Okay, even we can go ahead with hybrid configurations. No, I will take these hybrid configurations later, but first let me explain you some numerical. Any queries in this? Then I will go ahead with some half an hour numericals also I will explain you. So then it will be easy for you. Otherwise it will be difficult. So can we solve few numericals? Is there any queries in this? So can you take, madam, now you can unmute. Some few numericals I will give. So few numericals I will give them. So let them solve it. Then any queries are there, I will answer them also. Priyanka madam.
Yes, sir. No, sir, no.
Put them.
No any queries.
Some
Please start the numericals, sir.
numericals I will start few numericals. Then I will go ahead with hybrid. That will be better. Okay. So can we start this way? A 10 kilowatt of power is used by a household. Solar energy is incident on the horizontal surface at an angle at an average rate of 400 watt per meter square. 10 kilowatt power is total power is 10 kilowatt. Output power total power is 10 kilowatt, and solar energy incident on horizontal surface at average rate of 400 watt per square meter. Per square meter 400 watt is there. If 25% of this energy is converted to electrical energy, how much area of solar panel is required to supply 10 kilowatt? Can you start solve? I'll explain it if you're unable to solve. What he has given is, given data, try to see. Power used by the household, P is equal to P is equal to 10 kilowatt. Then per square meter solar energy incident, that is instant energy is, what is that? Incident energy means per square meter, the P input is 400 watt. Then efficiency of the solar is 25% is given. Okay, efficiency is 25%. Then area, if you consider A, then what I want, how many number of panels are required? So total cross-sectional area, how much is required? Can anyone say? Output power equal to how much? Or efficiency equal to output power by input power. So output power he has given, efficiency is given. In the input power, what is input power? Irradiance, watt per meter square, into area I need to multiply. A is unknown parameter. Can you solve it? How much area is required? If I want to have 10 kilowatt power, it is basic question. If I want at your home, if you want to build 10 kilowatt power, okay, one panel is 400 per watt meter square. One panel is 400 per watt meter square. Efficiency is 25% is there. So how much area your panel should have, or how much surface is required on your rooftop? Can you tell me? So power required is, P output required is 10 kilowatt. Per square meter it is 400 watt per meter square. Then efficiency of is 25% is there. So area required, how you calculate? Output power equal to efficiency into input power, or efficiency equal to output power by input power. So area will be how much required? So you know that yesterday we solved. What is input power? We have solved, no? How you calculated? This output power by input power. L into A. L is here, it is given. Tell me, excuse me. Excuse me. Can you tell me that answer? Is anyone trying or not? Am I audible? Excuse me. Excuse me, am I audible? Then okay. You are there. So can you tell me that answer? If you don't know, I will explain you. So how much it is? Output power is 10 kilowatt. Efficiency is 25%. So input power is area into watt per meter square. How much A you will get? Madam, is anyone solving or not?
So 100,
How much? Yes, 100 meters square.
100 meters.
Yes. So can you identify this one? What is the value of fill factor if maximum power is P max is 50 watt, open circuit voltage is 20 volts, and short circuit current is 3.5 amperes? It is one more question. What is the value of fill factor if maximum power is 50 watt? If maximum power is 50 watt, what he has given, P max is 50 watt, VOC is equal to VOC is equal to open circuit voltage is 20 volts. Short circuit current is 3.5 amperes. So how to calculate the fill factor? Fill factor is P maximum by VOC into IOC. So how much you are going to get? That means unshaded modules are how much percentage it is filled, we are going to calculate. P max by VOC into ISC. How much you are getting? Formula, do you remember? This formula is this one. This one. Fill factor formula is P max by VOC into ISC. So P max is given, VOC is given, I short circuit current is given. See how much it is?
So 0.71?
76%.
Okay, 0.76. Okay, sir.
0.76. Okay. Suppose a solar PV panel generates a global maximum power of 500 watt. We have taken P maximum is 500 watt at standard temperature condition. What is standard test condition? 1000 watt per meter square, 25 degrees centigrade. Now, a shadow of tall building is falling on the PV panel. Try to understand. A solar PV panel generating a global maximum power of 500 watts at standard test conditions. What is that? 1000 watt per meter square, 25 degrees centigrade. Now there is a shadow of tall building is falling on the PV module. So because of the shading, there is a reduction in the capacity of the module. So how much it is? Due to shadow of the tall building, there is output power is reduced to 300 watt. Then what is the mismatching loss? Can you tell me? Percentage of mismatching loss I want. So given is maximum power at standard temperature conditions is test conditions is 500 watt. Maximum power under shading condition is 300 watt. So what is the formula for mismatch power loss? Can you tell me? P maximum power at standard test condition minus P maximum power at partial shading condition by P maximum at standard test condition into 100. How much percentage? Mismatch loss percentage is how much? I am asking you percentage, not mismatch. Mismatch power is 500 minus 300. It is 200 watt. How much percentage it is? Excuse me. Mismatch power loss is, what is the percentage of mismatch loss? The formula is this. Mismatch power loss is difference between standard condition minus the power at shading condition. Standard condition is how much power we are generating? 500 watt. Power
So
at
40%?
partial. Yes, ma'am. So we are generating power at standard test condition is 500. Power at shading condition is 300. So the percentage is 40%. Difference of power is 200 watt. Now, suppose a PV cell is, now this one is little bit advanced. A PV system is to be designed to produce, we want to design a 350 watt at 34 volts. We want to design a PV system, okay, to produce, we want output power is 350 watt. Output voltage is 34 volts I want. The voltage at maximum power of one PV cell voltage is given. One PV cell voltage is 0.7 volts, and VMP of the cell, the okay, the current density of the cell is 340 ampere per meter square. VPV is of the cell is, one cell is 0.7 volts. The current density of the one cell is 340 ampere per meter square. Okay, using this data of the PV cell, we need to design a PV module consisting of, okay, considering it is operating at a maximum power point if each cell is 10 centimeters square in area. Can you solve? V maximum is 0.7 of cell. Current density at maximum power point is 340 ampere per meter square. Therefore, PV cell current is how much? Each cell is 10 centimeters square in area. Each cell has area of, every cell will have a area, no? Every cell has an area of 10 centimeters square. So the PV cell current will be equal to 340 ampere per meter square into area of each cell. It is how much? Can you solve? Is it correct? 3.34 amperes. Voltage he has given directly 0.7 volts. Current he has not given directly. Current he has given in terms of 340 ampere per meter square he has given. That too, each cell is 10 centimeters square. So 0.34 amperes I am getting. Have you got same? Yes, no?
Yes, sir. Yes, sir.
Power obtained for each cell. How much? Power obtained for each cell is voltage into current. 0.7 into 0.34. Isn't it? Power obtained for each cell is 0.2 watt. Now, now I want number of PV cells in the module. I want how many number of PV cells are required. If one cell is 0.2 watt, it is generating. I want 350 watts. How many cells are required? If one cell is 0.2 watt, it is generating. I want 350 watts of power. How many cells are required? Number of cells or number of modules, how many required? Excuse me. Try to understand. Vmax of one cell is 0.7 volts. Vmax of current of one cell is 340 ampere meter square. One cell consists of 10 centimeter square in area. So the cell current is 340 ampere per meter square into cell area, that is 0.34 amperes. Now total power of one cell is, per cell is 0.7 into 0.34, 0.2 watt. Now number of PV cells required in the module, how many? Total power is 350 watt.
750.
So the power required is in the module is 350 watt by per cell value. Okay, total power by per cell value. Total power by per cell value is 1750 modules are required. Now these 1750 modules, how many should be series, how many should be parallel? Can you tell me? Now I am having 1750 modules are there. How many can be series? How many can be parallel? Series, how you calculate? Can you tell me? I am having 750 modules are there. It is a series parallel connection. How many modules should be series? One cell voltage how much? One cell voltage is 0.7 volts. Total voltage is how much? 34 volts. Total voltage is 34 volts. Now, string voltage will be how much? Can you tell me? One string voltage will be how much? 34 volts. One string voltage is 34 volts. One cell voltage is 0.7 volts. How many modules required in one cell? Can you tell me? Number of cells in series will be total voltage by number of cells in the module. How much you are getting? Number of cells in the series will be equal to total voltage by per cell voltage. How much you are getting? Total voltage is 34 volts. Per cell voltage is series connection. How we have taken? Okay, let me take you here. Now series parallel structure only you take. This one you take. This total is 34. This total is 34. One cell voltage is 0.7. So how many number of cells are required? 34 by 0.7. How much it is? Number of cells. See, here is each cell is 0.5 volts. Total voltage is 4 volts. So total how many cells are required? 4 by 0.5, 8 cells I have taken. Now here I have 34 volts of total voltage, 34 volts. One cell voltage is 0.7 volts. So all the cells to be added. So how much amount of volt, how many number of cells should be in series? Excuse me. Number of cells in series will be how much? Total voltage by voltage per cell. How much are you getting? Excuse me, are you understanding? Number of cells in the series, what is total voltage by per cell voltage? Total voltage is 34, per cell voltage is 0.7. How much here?
So 48.57.
So 49 cells are required, isn't it? Okay, now 49 cells are in series. Okay, how many cells should be in parallel? How many cells should be in parallel? So 350 watt, 49 cells voltage is 49 cells voltage is approximately 34 volts. Now total number of cells are 1750. So how many more cells are required? Parallel combination. With 49 cells, I'm getting voltage is this much. So number of strings of 49 cells each will be connected is 1750 by 49. Is it okay? Number of strings of 49 cells. Number of parallel strings will be 1750 by total modules by 49. If I put 36 strings are required. So if you multiply 49 into 36 into 0.2, if you multiply you will get 350 watt. You understand? Okay, let me show you. Let me take you one numerical related to series configuration. You will understand that. Then I will come to series parallel. Can you take this if you don't mind? It will be easy. Design a PV array configuration which can generate maximum power point current of 9 amperes. Design a PV array configuration which can generate maximum power of 9 amperes at maximum power of 5 kilowatt at standard temperature condition. Also mention what kind of configuration used to draw the same. The PV module specifications are this: 315 watt, Pmax is 315 watt, VMP is 35 volts, IMP is 9 amperes, VOC is 43 volts, ISC is 9.77. I want 5 kilowatt power required. Current is 9 amperes are enough. It is which configuration? Total current is 9 amperes is enough. Total power required is 5 kilowatt. Okay. Current of each module is 9 ampere is there. Voltage of each module is 35 volts is there. How it should be connected? First of all, Can you tell me? I want maximum power of 5 kilowatt. Okay, and the current to flow through the entire all the modules should be 9 amperes is enough. Output current is 9 amperes. Output current is 9 amperes. Maximum current PV array should generate 9 amperes. PV array has to generate maximum power of 5 kilowatt. This is the condition. So what he has given? He has given VOC 43, ISC 9.77. IMP of one module is 9 amperes. VMP of one module is 35 volts. Now, single PV module specifications are, one PV module specification is one PV module is generating power of 315 watt, one PV module generating voltage of 35 volts, one PV module generating current of 9 amperes. Okay, number of PV modules, how many required for to generate 5 kilowatt? If I have one module is generating 315 watt, I want 5 kilowatt power. How many number of modules are required? If one module generating 315 watt, I want 5 kilowatt power. So how many modules are required? Number of PV modules required to generate a If single PV module is generating a power of 315 watt, number of modules required to generate 5 kilowatt power will be how much? Can you tell me? Total power by individual power here. Total power is 5 kilowatt. One module power is how much? With one module 350 watt I am generating. With all the modules I want 5 kilowatt. So number of modules required will be how much to generate 5 kilowatt? Total power by one module power, how much it is?
16 almost.
Yes, 5 kilowatt by 315 modules is 315 is 16 modules are required. Now the 16 modules should be connected in series or parallel. How it should be connected? So with 16 modules, yes, you can generate 5 kilowatt power. These 16 modules should be connected in series or parallel or series parallel. Can you tell me? He said 9 amperes only he want to generate, but 5 kilowatt power is required. So the 16 modules, how should be connected? In series connection, what will happen? The current through all modules is same, no? Voltage is added together. Okay. In parallel, reverse. The currents are added, voltage will be same. So which configuration I should go? Series or parallel? One module current is 9 amperes. One module voltage is 35 volts. I want output current of 9 amperes is enough. I want output current should be equal to module current. Which configuration I should go? Excuse
Series.
me. Yes. So terminal current will be equal to module current. When it is connected in series, current is same, voltage are added. So that's why, that means to get a terminal current of 9 amperes, all 16 modules have to be connected in series configuration. Is it okay? Do you understand?
Yes, sir.
Okay, no? Try to understand. PV array has to generate 9 amperes. Total PV array has to generate 5 kilowatt. One PV module 315 watt. One PV module 35 volts. One PV module current is 9 amperes. Okay. So when single module is generating 315 watts, number of modules required to generate 5 kilowatt is 5 total power by individual module power. So it is 16 modules is there. So but we want output is 5 kilowatt and 9 amperes. So which is possible? PV array current should be equal to PV module current, which is possible in series configuration only. Now if you multiply 16 into 315 watts into, okay, 16 into that 35 into 16 into 9 amperes. If you multiply also, you will get same. Last one, we'll see. Then tomorrow I will discuss you other thing. Now this one, can you take? Design a PV array. Design a PV array configuration which is generating maximum current. Which is generating maximum current of 83.36 amperes. Which is generating a maximum current of 83.36 amperes at maximum power of 4.1 kilowatt. Maximum power I want is 4.1 kilowatt. Maximum current I want is 83.36 amperes. Okay, at standard temperature condition. And per module voltage, per module currents are given. Voltage at maximum power VMP, IMP is given. VMP is 49 volts. IMP is 5.21 amperes. IMP is 5.21 amperes. VOC 59, ISC 5.5. P maximum is 255.29. Now, how to calculate? Can you tell me? PV array has to generate maximum current of 83, but with one cell, how much we are generating? 5.2. But how much I want? 83.36. PV array has to generate maximum power of 4.1 kilowatt, but one module 255 watts I am generating. So how many modules required? Number of modules, one module is
16 modules.
yes. So number of modules required is 4.1 kilowatt by 255, 16 modules. These 16 modules should be connected in which way, madam? Good, madam.
Parallel.
Yes. Why? Why? The current is more. So
Maximum current is
yes.
83.36.
So
So
when
in
I
parallel it will be added.
yes. So number of modules to be connected in parallel is terminal current of PV array by current rating of single module 83.36 by 5.21. 83.36 by 5.21, which will give you 16. Is it okay? This is a parallel connection. 83.36 by, this is 83.36 by 5.21, you will get 16 modules. So total current by individual module current will give you that modules, number of modules. Or total current is equal to number of modules, 16 modules into that current. Is it okay? Is it okay? Any queries now?
Yes.
Do you understand?
Yes, sir.
Any queries are there? Please let me know. I can answer. So there is series parallel connection, TCT connection is there. I will tell you those two numericals tomorrow. That won't be any problem. Then today, if you have any queries, please ask me in any numericals or in something. Excuse me. Do you understand at least? So what we discussed today, what we have discussed. So we have discussed about. Let me show you first. So today we have seen basic introduction to first one. We have discussed about, maybe these are the numericals. First one we have discussed about total architecture of a PV system, which consists of different shading conditions. PV panels are there, which are connected in different configurations. Now can you understand this? A PV system is there, different shading condition, uneven row, uneven column, diagonal shading, okay, and it can be connected in different configurations. Now what we are doing, we are checking IV PV curves, and we are calculating which one we are calculating, we are examining different parameters. Okay, so here what we is done is mismatching loss, efficiency, fill factor, and everything we are calculating. So initially first we discussed about different shading condition. It can be due to shading, can happen due to trees, buildings, clouds, or maybe snow. Then we have seen column shading or row shading we have seen, and we have also seen then there is which one? Diagonal shading we have seen, triangular and L-shaped shading or frame, random shadings we have seen. Then after that we have observed when irradiance is changing, the current variation will be high, power variations are very high. When temperature is changing, there is no much variation. Then after that we have discussed about different mitigation techniques we have seen. The first one is about blocking diodes as well as bypass diodes you have seen. Blocking diode is used to block the reverse flow of current during shading modules. Bypass diodes are used when module is shaded, which will bypass the power through the diode, which is connected as a bypass. So now here we have seen the curves. Then after that, when one module is shaded, how the power will be bypassed, how the current will be bypassed also we have seen through the curves. Then when it is a series configured system, it is the current is same as a module current and voltage will be summation of the all the voltages together. The powers will be same. In the parallel configuration, it is a low voltage, high current application. Then series parallel configuration. So in the series parallel configuration, in one string, all the modules are connected in series, all the strings are connected in parallel. So next bridge link we have taken. So there is four modules together will be connected at time. Four modules together will be connected at time. So here, next one honeycomb structure we have seen, that is like a B structure of every 6 modules. Then TCT is total cross state. So series parallel bridge link honeycomb total cross state will be with medium voltage, medium power applications. Ultimately, above all, TCT will give you best performance. This is what we discuss with the numericals also. Okay. So, is there any queries? Yes, you can ask me. Or do you understand today's one about shading conditions, about configurations? At least do you understand? Priyanka madam, are you there? Excuse me, is it fine? Or any queries?
No, sir.
Fine, no? Understood. No? Okay, then thank you. And tomorrow we will see.
Thank you, sir.
Uh, okay, fine. Priyanka madam, I can wind up, no? If okay.
Yes, sir. Hello, sir.
If there is no queries, then can I wind up? Is it okay?
Yes, actually, there is some internet issue, sir. So,
Huh.
not continue for interacting with you, sir.
But do you understand? Is it okay?
Yes, sir. Absolutely.
Fine. Okay, thank you.
Okay, so actually, you just describe all the things with numericals, and personally, my doubts is clear, sir. And I hope
Okay.
all the participants they clear this doubt.
Okay. Thank you. That's fine. Then tomorrow we will see hybrid configurations as well as then standalone and hybrid systems. I will try to explain you along with few more numericals on TCT other configurations. Okay. Thank you, ma'am. Thank you.
Okay, sir.
Thank you.
Thank you so much, sir. And so I declare today's session is concluded. Thank you, thank you so much, sir. I also thankful all the participants. Thank you.